Welcome to this video. I am Federico Formica, one of the developers of ATheNA. In this video, we will go through a walkthrough of one of the examples tutorials available online for ATheNA. Please check our previous video on an installation guide and an introduction to the ATheNA tool. We can now run ATheNA on one of the two examples provided in the repository. In particular, we will focus on the automotive example. The model in question is based on an air-to-fuel controller, in short AFC, for an internal combustion engine developed by Toyota. ATheNA is a black box technique and can be applied to any kind of model as long as it has a set of imports for the input signals and outports for the output signals. We can start by defining the requirement under analysis. Specifically, at all times between 11 seconds and 50 seconds, the air-to-fuel error must be below 0.007. This requirement is captured by two variables, phi and preds. Phi contains the Boolean expression that defines the requirement. The string contains all the temporal and Boolean operator. In this specific case, we have a global temporal operator represented by these two brackets that are limited by a temporal indication, in this case 11 and 50 seconds. In this interval, both the atomic predicates lower threshold and upper threshold must be true. In this case, they are connected with an AND operator. The variable preds contain information on the specific atomic predicates, so in this case, lower threshold and upper threshold. In our case, the system has three output signals, as we can see here from the three outputs. But we are only interested in the verification measurement, so in the air-to-fuel error that is represented by the first output. We don't, in this case, care about the other two signals. So an atomic predicate, it's always expressed in the way of vector A times output vector is less or equal than the scalar B. In this case, the outputs are, of course, the verification measurement, mode, and pedal angle. We only care about the first one. So the matrix A is, in this case, composed by 1 and 2 zeros. And here, in this case, we have our threshold values of 0.007. These two predicates basically are equivalent of having error less than 0.007 and error greater or equal than minus 0.007. To achieve a better union of manual and automatic fitness function, it is advisable to normalize both to be in the same range. For the automatic fitness function, this is achieved by normalizing the atomic predicates. So in this case, we have to set the normalized property to true and provide a value for the maximum automatic fitness value. These do not have to be exact. It can be an approximation as long as the values are comparable in the same order of magnitude. Usually a good guess is to use the range width for the signal under analysis. In this case, we are using this air-to-fuel error that we know should be between minus 0.007 and 0.007. Therefore, as maximum value of the automatic fitness, we use the width of this range that is approximately 0.015. Now that the requirement has been defined, we need to specify the assumptions on the input signal. Each input signal is defined by three elements: the number of interpolation nodes, also called control points, the range for each signal, and the interpolation function used to interpolate these nodes. In this case, the first input signal is the engine speed, and we use only one control point, a range between 900 and 1100. As interpolation function, we use a constant function. So this explains why we need only one control point. For the second input signal, that is the throttle pedal angle, we decide to use 10 different control points, a range between 0 and 61.2 degrees, and we use a piecewise constant interpolation function. ATheNA allows to define both equally spaced nodes or manually set nodes at specific time instant. In this case, we are not declaring it, so the system will use equally spaced nodes. So out of the 50 seconds that is the simulation time, we're using 10 steps, one constant for each 5-second interval. Now we need to provide, of course, a few additional detail. For example, we need to provide the name of the Simulink model under analysis. We need to provide also the simulation time that, as I said, was 50 seconds. ATheNA also supports test case generation for initial conditions, not only input signals. So we can use the variable initCond to define range for initial conditions. In this specific case, the model does not have initial conditions, therefore this variable is empty. We also need to define some MATLAB variables that are used by the model to define some parameters. In this case, we are using the default ones, and we are just assigning a value so the Simulink can access them. Now that both the requirement and the input signals have been defined, we have to focus on the search options for the ATheNA algorithm. These search options are contained inside this object, ATheNA opt, of class ATheNA options. ATheNA options inherits all the properties of the Staliva options objects and add additional ones. For a full list of all the available options, what do they represent, what is the default value, and what values are acceptable, we recommend checking the ATheNA options.m and the Staliva options.m files, as they contain a more detailed documentation. Out of all the options that I have defined here, some of the most important ones are, of course, the number of tests that is set to 50. This means that the algorithm will generate at most 50 iterations per each run before giving up and returning the non-failure revealing but with lower robustness test case. This parameter is also very important because it is used in a linear combination of the automatic and manual fitness values. Specifically, this is the weight of the automatic fitness function. By setting it to 0.5, we are saying that we want to prioritize equally the automatic and manual fitness. Therefore, the ATheNA fitness will be an algebraic mean of these two values. Of course, we also need to define the manual fitness function. In this case, we are providing the handle. We will see soon how this manual fitness function is defined. And we decide to do only one run of the algorithm. Each run is independent from the previous ones. And of course, since ATheNA is a stochastic algorithm, the result of each run will usually vary depending on the number of iterations before finding the test cases and, for example, the test case found. Regarding the fitness function, we decide to use this fitness function. All manual fitness functions must have the same basic structure. They should take as argument 3 input variables: the time array, the input signals, and the output signals. And they should return a single scalar value called fitness. In case more informations are needed to actually run this, one can always use global variables to access other information. In this case, we decided we want to test, we want to prioritize test cases that have a low throttle between 10 and 50 seconds, as this is a potentially critical situation, as the engine must provide a minimum amount of fuel to keep running, but this might create problems for the air-to-fuel controller. So we decide to pick as fitness value the minimum value of the throttle in the range 10-50 seconds. This value is then scaled using the throttle angle range. This way, this fitness value would always be between 0 and 1, and therefore will be compatible with the automatic fitness, that it's always between -1 and 1. We can now run ATheNA, but first we need to add this folder to the path. ATheNA is now showing us all the test cases that it's trying. We can see on the left the input signals and on the right the output signals. Specifically, remember that we want to check the air-to-fuel error, that is the first output. So this is the plot we have to focus on. In the command window, we can see the progress of the different iterations and the fitness values they produce. These values are updated only when the best ATheNA fitness is found. Okay, so now ATheNA has finished and has found a failure revealing test case in 26 iteration. If you put scopes in the model, you can quickly see this failure revealing test case, because of course the algorithm stops when it finds a failure, and therefore the last test case tried by the algorithm will be still memorized in the scopes. So here we can see these this failure revealing test case, and probably we can see that here this is the failure area where the signal U went below the -0.007 threshold. Of course, ATheNA also returns a history and results variable that contains more detailed information on this test case. If we open the results variable and the run field, we have some more detailed information about this test case. Specifically, we know that the best test case, that in this case is failure revealing, had a automatic fitness of -0.02, a manual fitness of 0.009, and an ATheNA fitness, so a combination of these two, of -0.0057. We know that it finds a failure revealing 26 iterations. That this parameter says that the falsification has been successful, so falsified is true because this is a Boolean parameter, and it finds a failure in 117 seconds. The field best sample actually contains the value of the control points that we can check, and the param_val variable contains a time array, again the control points, this is the same as best sample, and the output of the model for the failure revealing test case. Therefore, we can use this t and y variable to pinpoint exactly when the failure occurs and see the behavior of the system before the failure happens. On the other hand, the history variables contain not summary information on the test run, but it contains information of all the test case generated and all the fitness values associated with these test cases. This is very useful because it allows you to see if the ATheNA fitness and the manual fitness and automatic fitness are decreasing together, or if maybe there are unexpected behavior where one decreases and the other increases. This is all on executing ATheNA on a Simulink model. Thanks for the attention.